Neuroscience and Technology. I'm Kevin Castle, and welcome to the Humanity Podcast, where we inform and empower the public through powerful dialogue with IT visionaries. Joining me today is Helen Põldsam, co-founder and CEO at Cellaccura Biosciences, a biotech company developing precision gene therapies for central nervous system. She will discuss current technology and innovations in the neuroscience field. Prior to Cellaccura, Helen was co-founded a company that turned into the leading B2B accelerator in the Bay Area called Alchemist Accelerator. Helen holds a bachelor and master's degree from Harvard University. Helen, welcome to the Humanity Podcast.
Thank you for having me. Great to be here.
That's an absolute pleasure, and I appreciate you making the time to talk to all of us.
Sure.
So I thought it would be good just to get started, since we'll be covering the topics and the intersections of neuroscience and technology, to give a little bit of background about yourself.
Yeah, of course. So as you mentioned, I'm the CEO and co-founder of Cellaccura Biosciences. It's a Caltech spin-out company that develops precision gene therapies for the brain. You also mentioned Alchemist Accelerator. Mm-hmm. So while running a company that turned into Alchemist Accelerator, what I learned about myself was that rather than witnessing all the innovation happening, I wanted to be the one innovating. So I went back to school to do my master's, and this is when I first got interested in neuroscience while conducting research and prototyping technologies for learners with intellectual disabilities. So I started talking to people in the neuroscience field, and it became obvious that neuroscience was going through a disruptive change and was moving from a predominantly academic discipline to a field where we could start solving practical problems. And that's when I decided to venture into the biotech world to look for interesting opportunities at the intersection of technology and neuroscience. So I worked on a few projects to gain experience in biotech. And then at the same time, I started looking into different ideas with Dr. Alan Herman Poole, who is a postdoc at Caltech and now my co-founder. So he came up with the solution enabling cell type specific brain therapies. And we both thought it was an exciting opportunity. And this is how Cellaccura was born.
I got you. And so Helen, was your decision to go back and get your postgraduate degree, was it, were you already interested in neuroscience because of what you were seeing in work in the field, or was it once you decided you chose your major and then go down that path?
So when I went back to school, I was actually interested in educational technology, but my work with the kids with intellectual disabilities is what sparked my interest in neuroscience.
I see. Okay. And so when you were in the program and then consequently from what you've seen now, I mean, is there a big change to how neuroscience is being, from a practicing perspective? Is it different now with technology? Is it like, why don't you share kind of how the way that things used to be and kind of the way things are these days in the neuroscience field?
So, so neuroscience has been really going from like strength to strength during the past decade or so, mostly thanks to several technological revolutions. And among those are big data analytics, brain recording technologies, molecular tools for controlling brain function, cell profiling technologies to understand sort of the building blocks of the brain or neurons. And sort of the confluence of those technologies have enabled us to do things that would have seemed like science fiction maybe 10 years ago. And to give you sort of a sense of the magnitude of the disruption, about 10 years ago, we were able to record the activity of only a few brain cells or neurons at a time. But about a month ago, the neuroscience field reached a milestone where we could record 1 million neurons in a single organism. And in terms of why this is important with respect to how the brain works, the useful parallel to think about is watching a movie and trying to understand the plot of a movie by observing only a few pixels versus 1 million pixels on the screen. And of course, to deal with these reams of data that we can now get from the brain, high throughput data analytics has become indispensable for the field. And there are some nice examples that we can talk about where thanks to data analytics we have gained exciting insights to the brain.
Oh, interesting. Well, let's go into that. So what have you guys discovered as you guys have been extracting out this huge volume of data where before there wasn't, you didn't even have the opportunity to digest it and understand? What are you guys learning now?
Mm-hmm. So I think the decoding of the content of consciousness based on brain activity is a nice illustration of that. One early example that comes to mind is from Jack Allen's lab at UC Berkeley, where they used fMRI imaging to monitor whole brain activity while humans were watching movie trailers. And fMRI is an indirect way to measure brain activity. But what was impressive is that they established a semantic map of the brain, essentially showing which parts of the brain are active when humans see different categories of things, like a car, a bird, another human. And what you could do with this semantic map is build algorithms to start decoding what humans perceive solely based on brain activity. You could almost think of it as an involved mind reading exercise. So, of course, to be fair, fMRI is very crude tool, and accuracy of what humans actually see can vary quite a bit. But we can dramatically improve these brain decoding applications by recording data straight from brain cells. And again, there are several examples of that, but one impressive example that I've seen comes from Zhao Lab at Caltech. And they worked with monkeys, and they recorded activity from neurons in the brain region responsible for face processing.
Okay.
They wanted to know how the brain encodes information about faces and whether we can reconstruct faces we see only based on reading the brain activity. And that's essentially a supervised learning problem where we need to learn how face responsive neurons respond to different facial properties. So once they had constructed the model linking facial features with activity of specific neurons, they were able to flip the algorithm and reconstruct faces encountered solely based on the activity patterns of these face responsive cells. I think the surprising thing was that we can precisely recreate the faces monkeys see by listening in on only 200 neurons in the brain. So these are just a few examples how far the field has come in terms of really understanding the algorithms of the brain, and data science has been an incredible tool here.
So Helen, so just so I make sure I understand, given the enormous complexity of this topic. So you're saying that with only 200 neurons measured, you guys were able to the team was able to understand and recreate an understanding of what faces we're seeing, and they were able to actually replay that back, or was it more of just a read?
So they were actually able to recreate the face that the monkey saw. It was it was almost identical to the photo that the monkey was actually looking at.
Wow, that's fascinating. Right, when we jumped into this conversation, I would have had no idea that we would be that advanced, or that with just 200 different data points all correlated in some way to reverse engineer out an algorithm that we'd be able to reconstruct a face. That's fascinating. Wow. Where do you think, Helen, is the technology helping the most, right? Is it really on the algorithm understanding, or is it really being able from a physical understanding of what's going on in the brain? Is the technology advancement there? Like what's leading right now? Or what's limiting, I guess?
That is a good question. I think it's really a combination of a lot of different technologies. Big data analytics is definitely incredibly important because otherwise we would not be able to make sense of the large amounts of data that we are recording from the brain. But also, in order to sort of better understand the brain and start reprogramming the different functions of the brain, we need different like cell profiling technologies like single cell RNA sequencing, which enables us to profile all the genes that are expressed in each cell in a particular brain center, and also sort of different tools to control brain function, which are like optogenetics, gamma genetics. So yeah, I would say it's a combination of a lot of different technologies.
Okay, interesting. So I guess given the topic of understanding what's going on in the brain and being able to recreate what's going on, interpreting that, I guess one of the questions I have, which most people are pretty familiar with, is Elon Musk's company Neuralink. So are you familiar with any of the work that's being done there, and does it correlate to anything similar with the example that you've just given as well?
Yeah, I'm familiar with what Neuralink is doing. So so I guess Elon Musk's aspiration is to keep humans relevant in the age of approaching singularity, and one way to do that is to build efficient brain-machine interfaces with rapid information input-output. So I think one of the key topics to tackle here is whether brain-machine interfaces for healthy people is going to be gimmick or a true game changer, like the internet or smartphones were. And so what is impressive about their prototype is the hardware and data transfer solutions that they have built, and they can reliably record brain activity from hundreds of neurons for long periods of time, and that was previously a challenge. But I think there are two major issues that I could think of. First, they advertise their solution as a general read and write device for the brain, but crude electrodes are not that useful for writing information to the brain. Instead, I think we need technology that can write information at a cellular resolution. And there, like most likely it's going to be an optical solution, at least that's what neuroscientists think. And there are some cool applications that different labs are working on already. So there is hope that we will have something that will work in the future.
Interesting. And Helen, just from a future perspective, I mean, do you think that is a realistic, I guess not the doom and gloom nature of the belief of, this is a necessary technology step or we're going to become irrelevant, but do you think that we're going to be able to have that strong link and be able to actually imprint on the brain different things and be able to pull out information as well? Will we be able to have that bidirectional, feedback loop?
So I think currently there are definitely a lot of technological challenges that we need to solve. Like another one is, I guess one of the questions is whether it's feasible to create general reading and writing application in a single location in the brain, because like different brain regions are often highly specialized, so that you will most likely not be able to read and write any other information apart from what is directly relevant to that brain region.
Okay. So is this something that we can expect in our lives, right? That type of an interface with that type of read-write ability, and even understanding what's going on from a brain processing perspective?
I think it would be really challenging.
Okay.
But I mean, never say never, right?
Okay. All right.
Technology is advancing so fast that it's almost impossible to predict what's going to happen in 10 or 20 years.
So I guess, have you been surprised in the last 10 to 20 years, right? Or for the last couple of years from what you've been seeing, right? Are you seeing things that are moving quicker than what you would have expected in the trajectory of an advancement, moving faster at a quicker pace?
Yeah, absolutely. I mean, even the things that we are trying to do at Cellaccura, we couldn't even imagine doing something like that 10 years ago.
Okay.
And yeah, to the extent we understand brain and brain functions and brain cells, definitely it wasn't imaginable like 10, even maybe 5 years ago.
Wow. Okay. Okay. Well, why don't we just transition and talk to that? So tell me about Cellaccura Biosciences.
Yeah. So we at Cellaccura, we develop gene therapies for neurological disorders, and the basis of what we do stems from the fact that the same way we can program computers, we can now start reprogramming the brain. And a major revolution that has paved the way to this has been really the development of the understanding of the diversity of the building blocks of the brain, or neurons. So during the last few years, our understanding of the complexity of the brain has dramatically changed. So we know there are about 100 billion cells in a human brain, but in 2018, we didn't know whether we had a few hundred or a few 100,000 different types of cells.
Okay.
Today, we know that there are a few thousand distinct cell types in the brain. And that has really transformed how we look at different neurological disorders.
Interesting. All right. So is this a technology that you guys had started with, or is this something where you guys have taken the technology and have it rolled in from an application at a therapy level?
So the specific technology that we are using, that was developed by my co-founder, Dr. Alan Herman Pohl, and
Okay.
that sort of that allow, yeah. So we have a patented technology that we are using in our company, which is like high efficiency cell type specific gene therapy.
Okay.
But it is like CRISPR based, and we've been able to take advantage of several disruptions in the neuroscience field.
So how do you, okay, so I'm curious to understand, what are some of the success stories you guys have had using this technology?
So we are very early stage at this point.
Okay.
We are preclinical, but we are working on disease proof of principles for chronic pain and epilepsy. And in the future, we are definitely planning to add additional neurological and neuropsychiatric disorders.
I see. I see. And so how do you approach rolling this out, right, and having broad application in the market?
So we pretty much, like any therapeutic company, we need to go through clinical trials. So first we need to show that the technology works in mice, in monkeys, or in dogs, and then we can move to humans, and then we need to go through phase 1, phase 2, phase 3 clinical trials.
Okay. Okay. And so what do you guys think will be the result, right? So you mentioned a couple of different areas for chronic pain management, epilepsy. So what do you think the outcome would be once applied? What are you guys aiming for?
So, I mean, we're aiming to get rid of these different neurological disorders that really people have not been able to solve so far. So, for example, chronic pain patients, that they wouldn't feel the pain, or with epilepsy patients, that they wouldn't have these seizure episodes. So that's really the ultimate goal.
Interesting. Okay. Okay. And in terms of, as we talked earlier about the technology to understand what's going on in the brain, to measure, how, I guess, at what levels are you guys measuring the impact and success once it's been deployed, right? Is it at a cellular level in the brain, or is it more just understanding the outcome of the patient's particular case and pain or experience?
So yeah, for actually there are different levels for the technology, like to whether the technology works or not. This is definitely something that we measure on a cellular level, okay. But whether the technology is useful for patients, we need to measure that based on patient outcomes, really.
Okay. Okay. And so where are you at from an overall company perspective in your journey? You mentioned go ahead. Sorry, I didn't mean to interrupt.
Yeah, no, I mentioned we are pretty early. So we are funded by non-dilutive funding sources. We have some funding comes from Caltech, some from NSF, for example, and we are planning to continue to fund our operations from non-dilutive sources for a few years at least. And yeah, we are sort of like a recent spin out from Caltech. So as I said, very, very early at this point.
Okay, neat, pretty neat. And from a technology perspective, are you guys doing anything with from a data science perspective or algorithm understanding perspective, or just kind of trying to understand the brain so that you understand from a gene therapy application perspective where to deploy as well?
So yeah, data science is definitely something that we are using on a daily basis. And sort of to bring an example, maybe how we use data analytics in finding new gene therapy targets in the brain. So one of our, as I mentioned, one of our initiatives is to identify and pre-program cells in the brain that mediate pain relief. And so although we know the relevant brain centers for that, we don't know which cell types in these centers actually mediate pain relief. So, but what is cool is that these different cell types in the brain differ by which of the 20,000 different genes that we have in a mammalian genome they express, or which of those genes are active in each cell type. So what we first do is we profile gene expression with high throughput sequencing to find out which genes are expressed or active in which cells. And yeah, and then we can think of cells as entities in gene expression space. And cells that belong to a single type are clustered together in this 20,000 dimensional gene expression space. And we use graph-based clustering algorithms to discover the number of cell types in that brain region, as well as which cell types are activated during pain relief.
Interesting. Okay. All right. Fascinating, Helen. It's fascinating. So I guess one last question as we're talking about Cellaccura is, how important is a solid technology understanding as you guys look to create the therapies that you're discussing, right? I keep thinking you have this neuroscience background and there's a ton of research being done, but you also have the intersection from a technology perspective, right? So how critical is that to your company's success on the technology side from a data science or algorithm perspective, like versus understanding the gene the pure gene expression development, things like that?
It's critical, I would say. We would not be able to do what we're doing without having solid background in data science and sort of understanding how different algorithms work. So yeah, I think overall, today neuroscientists have to have solid background in data science. So they really need to understand biology as well as data science.
Interesting. And was that the case 10 years ago or 5 years ago?
No, absolutely not. 10 years ago, I don't think neuroscientists who were working in a wet lab used any data science tools.
Interesting. And have the academic institutions, are there programs set in place for people to have a dual focus understanding and get an education on both?
Yes. I think, yeah, universities have developed their programs keeping in mind that people need to have solid background in computer science and data analytics, and they offer more and more courses in that field as well.
Oh, interesting. Okay.
Yeah, and actually a lot of neuroscientists like nowadays go and work as data scientists afterwards, assuming if they choose not to go in academia, for example.
Oh, interesting. Okay. All right. Well, this is a fascinating topic, Helen. I appreciate you sharing thoughts, especially understanding where you're at with Cellaccura. I appreciate that. One last thing that we spoke about before today's podcast was European Innovation Academy. So I'm curious to if you could share with us, give us a little background. What is their focus of the European Innovation Academy, and what was your experience?
Yeah, sure. So European Innovation Academy is an intense 3-week program during summer for college and graduate students. And hundreds of students really come together from all over the world for this extreme accelerator to build startups. It's a very focused, hands-on, team-based learning experience. The program starts with forming teams and coming up with problems to solve with people you don't know and who come from different cultures. Then it loosely follows the lean startup methodology with the goal to translate your ideas into products and services. And then the program ends with pitch training and an opportunity to pitch to VC investors. And I was a mentor in that program for a few years. So, but yeah, the program is pretty interesting because as you can imagine, students go through a lot of sleepless nights.
Yeah.
Often their ideas change, and it's like a complete chaos at first, but somehow it ends up working out, and students, are able to come up with products that have been validated at least to some extent in the real world.
And who's backing this academy?
I think they have corporate sponsors for that.
Sponsors. Okay, interesting.
Yeah.
Interesting. And any success stories that you've seen come out of this program?
Yeah. So one of the success stories is a company called the Rheinsplanner. They are based in Austria, and they got started a few years ago. It's a platform for different clubs, like soccer clubs, music clubs, to manage different aspects of running a club, like members, financials, inventory. And today they have more than 3,000 clubs on the platform, and it's one of the largest platforms for club administration in Central Europe. So I think that's pretty impressive. And also, Entrepreneurship Innovation Academy works with existing companies, and they help those companies become more innovative as well. So one of the companies they work with is Scoro, which is a work management software for businesses. And since then, the company has grown to have thousands of customers in more than 60 countries, and they actually recently closed the 16 million Series B round.
Oh, wow. Okay.
Yeah.
Wow. So a number of success stories. Oh, that's fascinating. And overall, your experience and from what the students take out, I mean, have you guys, from people that didn't have necessarily a business success that came out of it, was there a mental or mind shift that the students came out of this with? Because I can imagine if you're saying you've got to go through all those steps, you do it over a short cap period of time, that's definitely a time of rapid change for every person. So what did you see in your role in that organization from an impact of the kids themselves?
Yeah, so this program really gives the students a framework to follow to sort of eventually get to a product that addresses an actual need. So you don't really need to reinvent the wheel. You have a methodology that gets you there. And it teaches how to find and define which problems are worth solving, how to generate a solution, and then form a team that can build that product. And finally, how to iterate fast based on feedback. And what is nice about this framework is that you can apply to develop your own startup as well as for innovation inside a large corporation. So it essentially prevents you from wasting like a year or half a year building a product that nobody needs. So yeah, I think students walk away from that program with transferable skills that will help them become really innovative problem solvers in pretty much any path they choose to follow.
Right. Yeah. No, that makes perfect sense, right? From an entrepreneur perspective, obviously that's right. It's an obvious path that you're going to have to learn and develop those skills. But from a corporate perspective, in any role would also follow through as well. So that's fascinating. Well, Helen, I know that this is the first time we've had the topic of neuroscience on the show, and I appreciate you translating and sharing with us the all of the innovation and technology investments that's going on in the neuroscience field and where it's leading to, and as well as the work that you're doing at Cellaccura. So I appreciate your time today. And thank you for listeners for tuning in. I hope you've gained some valuable knowledge today. Subscribe and send us ideas if you want to see in future shows. I'm your host, Kevin Castle, and thank you for listening.